Alright, so for the next practical lab that you have to submit, let's go through the worksheet. We are going to be doing this problem lah. So let's take a look. The plier below is made with malleable cast iron, and it has a steel pin. So let's determine the plier safe clamping load if the safety factor is about 1.2. And so this is part 1. You need to determine the safe clamping load. And what is the clamping force magnification ratio? For example, if the user clamps by 10 kilo, so if the user applied 10 kilo here, what will be the clamping force over here? So if it is 40 kilo, so it has a 4x lah, magnification. Next, we need to determine what is the pin reaction force. And bonus, if you can determine what is the load that causes the deflection at the handle to contact here. So this is bonus lah. So let's go one by one. Number 1, you need to download the CAD file from your VLE and open it up. So you're going to see something like this lah. So there are, I think, 3 files. We don't need to model the bolt. We can delete this bolt lah. So this bolt is not necessary to be analyzed. So you can close it and delete this bolt lah. Let's start by File, New, and create a new assembly. So click OK. So this is an assembly. You need to browse the part. The parts are in pliers first branch. So this is your plier lah. You can put it somewhere and then go back to assembly and then insert more components, browse. This will be the second branch, so this one. So you can drop it somewhere or you can immediately rotate it. For example, X, and I click X again, it will rotate again lah. So this looks nice. It is aligned properly with my assembly. You can move the components. However, the first component you cannot move lah. Why? Because it is F here. F means it is fixed. If you want to modify this, you can go right click here and then click float. So now you can move the first components lah. So however, in assembly you need to fix something. So you can go back to the first branch and then click fix. So this is cannot be moved anymore. The second component can be moved lah. So next thing, we need to assemble it. So commands in SolidWorks, you need to click mate, choose concentric, and then choose the hole, and then choose the other hole that you want to align it to. So this will fall under concentric, and then click OK. So now if you move the component, it will move according to the axis of the rotation lah. However, it travels like this. So you need to do one more mate, which is coincident. You want to coincident this surface to this surface lah, so that it is touching. So now your assembly has been completed. This thing is able to move. And again, you need to be careful and make sure you don't have any interference lah. For example, like this, I have interference. If I go to evaluate and click on interference and I click calculate, it will tell me the 2 locations where it has interference lah. So if you go into your simulation like this, this red color part will be joined together lah. It will be bonded together. And of course, again, you need to treat coincidence as interference. By right, I should be getting interference detection, treat coincidence as interference, and then calculate. I have here, I have first branch, second branch. Is it not rubbing? It should be rubbing. Interference detection, treat coincidence as... Okay, I think I gotta move this a bit first. Interference detection, treat coincidence and calculate. Now it will show. It will show this surface as touching to each other. So this particular surface, if you go to simulation and immediately create a new study under static, it will create something called a global contact bonded lah. So where is it bonded? It is bonded at here lah, interference detection, calculate at here. So you have to do something. You have to delete that contact. If you go here, global contact bonded. If you run your analysis as is with global contact, this means that the two surfaces is already welded together. So you gotta right click here and then click delete. Click yes. So now there is no connection between the two components. You need to create the connection. The most appropriate connection is something called a pin. So you can right click here, connection. It's not spring, it's not bolt. I think the best one is pin. Click pin. So pin, you need to select the blue color, one of the holes here, and the pink color, the color at the back here. So there is an option of with retaining ring, meaning no translation lah. So the pin does not move horizontally along its axis. And there is an option for with key, meaning no rotation. So you don't turn on this one lah, unless you have a problem with motion. Currently, I choose not to turn on this one. You can include things like strength of the pin. You can include things like torsional stiffness of the pin if you want. However, I'm not interested in the torsional stiffness of the pin. It's nothing there. So click OK. So now the pin will be created. So this pin is under connectors and there's a pin connector. So now your both of the components are already connected to each other. So next we need to assign the material for the first and second branch. Right click, apply, edit material. Currently it is iron lah. I don't have a lot of options. I just choose this one, malleable cast iron. So you need to take note what is the yield strength. Screenshot. Yield strength. Let's go to your practical lab. Let's put on a new slide. So this is the material data. And then click apply and then close. So you have malleable cast iron. Oh, it's very black color. So since the material property is like this. Okay, next, what do? We need to apply some load lah. External load, right click, you can apply force. Maybe you can apply at this top surface and then also at the bottom surface. So I've got two locations. How much do I want to apply? Maybe I want to apply 1000 Newton. Let's try 1000 Newton. And now it will be per item lah. So top 1000, bottom also 1000. If I click total, then top is 500, bottom is 500 lah. So I should not do that. I should click per item lah. And then I'm going to click OK. So I've got a force there. However, you can imagine if you're doing this test inside your testing laboratory, if you just push this part, this thing will just move lah. This thing will close and then move. So you don't want to do that. You are currently doing a static analysis, so you might want to consider gripping something. So when I say gripping something, you need to assign some boundary conditions. The most appropriate one would be this one, fixed geometry, meaning the clamping surface is not moving lah. So these two surface is actually not moving, so it's like gripping something lah. So you can click OK. So now you can create a mesh. And of course you might want to take a look at the mesh quality. Click details. My quality is about 96.6%, is less than 3. I can always go to create mesh plot and check my aspect ratio. Where do I see some problems? I see some problems here. If the problem area is not really that critical, then you can avoid it lah. The highest one is about 19 aspect ratio, so it's not really that good lah. You might want to mesh again, create mesh again, and then click the slider a bit, and then see have it done any improvement on the mesh quality. Slight improvement. Now it becomes 14. But then again, this 14 is just at certain area lah. If you feel it's not really important, that area, you can simply proceed lah. So I have done this and I have done that, and then let's run the analysis. So I can see here the deformation scale factor is like 7.99. So I can check my animation. So it bends like that lah. So it is gripping the component, so it's not moving. And then I can slow down the animation. Okay, so next I might want to check my displacement. Displacement is about 1.8 millimeter only lah, so it's very small. So 8 times deformation scale factor. Why do we do that? Because we want to see how it deforms lah. So let's check. Is this component good enough? I can of course edit my definition, change it to megapascal, change my numbering to general, and show my mesh and show that it is in discrete, and then click on OK. And of course I cannot see anything lah. So if you see something like this, you might want to hide one of the components. How do you hide them? We have to hide them in the assembly lah. I got my first branch and I've got my second branch. So maybe I want to hide my second branch. Click hide, and I go back to my static, and I gotta show back lah my stress. So my stress is like this. Does it make any sense? 1.54. It's very high. It's very high lah. So I might want to click this, and then I lower it a bit first, maybe 500. Obviously I've got this particular regions 500 megapascal. How much can this thing last? So bear in mind this is actually cast iron. So cast iron. So cast iron typically will fail using brittle failure. Why? Because the material is brittle. It's not like steel, S-T-E-E-L, right? Steel, it's different. The failure mode is different. Steel and aluminium, the failure criterion is yield. Do we call it yield? I suppose it is brittle failure, and I think we call it ductile, right? Ductile failure. Why? Because steel will undergo necking phenomenon lah before it fails. So ductile failure, typically we will use yield stress. However, for cast iron, it is under brittle failure. It does not undergo any necking. If it were to fail, typically it will fracture. This is a catastrophic fracture. Meaning the failure, you don't use yield stress lah, you use tensile strength. So there are two different failure criterion lah, so you have to be careful lah. Is there any safety factor here? Safety factor is 1.2. So for cast iron, safety factor is equivalent to tensile strength or ultimate tensile strength. Ultimate tensile strength divided by stress maximum. So what do you get? 1.2 is equivalent to, use this one lah, use tensile strength. 3.6, wow, that's a lot lah. 3.6, 413 megapascal divided by sigma max. So sigma max should not exceed 413 divided by 1.2. 344 megapascal lah. So your stress value anywhere on the plier should not exceed 344 lah. So let's try. Keep the annotation. I'm going to add one more slide. Let's go back here. Are we getting 344? How much are we getting? I can click plot tools here, probe my values somewhere around here. 700 something already lah. So you need to determine what is the proper force that this plier can achieve lah. Again, so currently I put 1000 and I'm getting about, I forgot already. I'm getting about 700 something. You need to keep it lower at about 344 megapascal roughly lah. And again, your results should not include locations where you have a high stress concentration factor. So you have to be careful a bit. You have to move slightly further away, maybe here, 500 something. Reasonable. So if you want to look inside the stress plots, you can, for example, you want to look at section clipping. Just have to drag it until you see some values. Oh, that's a little bit far. Then you can see some values. This is the internal lah. If I were you, probably I would probe somewhere inside lah, away from the corner. Don't take the corner. If you take the corner, it's going to jump very high sometimes. 800 something. But then again, corner is a location where fracture will happen. Somewhere around here is about 600 something. 621. Where is it? At here, this location. So depends lah. If you want to be safe, you can take values at the corner lah. If you want to be more less conservative, take values away a bit. Because CAD, you have all these sharp corners lah. You cannot avoid it. In real life, maybe you want to do some radius here. You will avoid all these problems. Currently, my stress, it has been under section clipping. So if you want to turn it off, click this one, it's gone, huh? It's gone. Okay, so what else can we do? You can always look at ISO clipping, drag it to determine the places where you have problems. And of course, answer some of the questions lah. Safe clamping force and what is the pin reaction force. So next thing you can find out what is the pin reaction force. You can go to right click here, list result force, and then there is something called reaction force, and there is a connector force. So if you look at connector force, it will show you the only connector that you have lah, which is the pin. The shear force is about 3000 Newton lah, 3000. And if you go to reaction force, and then you have to select for example this one, click update, you can see that the value of the force here is about 1.9810 to the power of 3, so about 2000 Newton lah. So you give a 1000 Newton clamp force, the clamping force has been magnified by this much. So now you can calculate how much is the clamping force magnification ratio. Other components, these are some things you can determine. Determine the force that causes the deflection of the handle up to contact. It becomes like this. You can run it again. Play around with the deflection. Then again, of course, we get high stress value because we are doing linear static analysis. Alright.